So we're going to see how to solve systematically the first sets of differential equations that we're going to see in the course. We're going to start with something called separable equations. Separable equations are going to be, in this course, we're going to see first order separable equations, and they can be linear or nonlinear. If they're separable, they're going to be easy to solve. In fact, this is the ECS to solve differential equations. All that you need to know to solve these equations is to remember how to integrate, which of course you all know because you've taken a course that taught you how to integrate almost everything, right? So anyway, the only requirement for this particular part of the course, to solving separable equations, is being able to integrate, okay? So hopefully remember your integration. If you don't remember, have it handy. Have handy a table of integrals, so you remember how to do integrals. I'm not going to be solving integrals in this course. All the integrals that we will have will be very easy as compared to the integrals you've done in the previous course, but you do need to remember how to integrate. All right. Now, what is a separable equation? A separable equation is an equation, again, first order, so only one derivative. Means it's an equation that it can be written in this form. By that I mean you can put all the y's on the left, all the x's on the right. By that I mean all the dependent variables on the left, all the independent variables on the right. Now, we're going to do many examples, right? This ny is an arbitrary function of y, mx is an arbitrary function of x. Now, we're going to see how we solve this in general, and then we will do several examples. That's what we're going to do today. And by today, I mean this video. Okay, generalize today. Now, there's the proper way of doing it. That's the way you have to do it if you want to be mathematically correct. There's the fast way to do it, which is very algorithmic in a way, but it's non-rigorous in the sense that you do something like multiplying by a differential that a mathematician would, probably you would make a mathematician cry if you do it in front of them, a pure mathematician. Anyway, we're going to learn both ways of doing this, and the way is the proper one. Once you know what you're doing, you're allowed to do the fast one, okay? But you need to know what you're doing. Now, how do we solve this? How do we transform this into, you see, remember what the problem is. We want to find y of x. This is what we want to find. And we have an equation that involves y dots, the derivative of y with respect to x, involves a function of y and involves a function of x. So we want to find y of x. All right, how do we transform this differential equation into a problem of pure integration? Well, easy. Now, we have all the y's on the left, all the y's on the right. What we're going to do is integrate with respect to x on both sides, all right? So integrating with respect to x on both sides, I get ny dy dx equals integral mx dx. All right. Now, you may be tempted to say, right, the differentials cancel. But that's kind of the part, this is the fast thinking. Differentials do not cancel. I mean, in practice, it's a good recipe to do the calculation fast if you know what you're doing, but please don't do it like that. The nice thing is, what you need to do is to remember a little bit of your previous calculus and say, oh, I recognize this. This is the differential of the function of y of x. What is the differential of y of x? Well, you learned dy is equal to dy dx, the derivative with respect to x dx. This basically tells you how, the intuition is, if I increase a little bit x, how much does y increases? Well, just a little bit, but how much? Well, the slope, right? You multiply by the slope, the small interval, the small increase in x, and you get a small increase in y. Anyway, this is the differential of the function y, and look at this thing. This is literally the differential of y. Wonderful. That means that with the proper way, what we get is that this gets transformed into my dy, and then equals mx dx. Right? So now, wonderful. We have an integral on y on the left with a function of y only, an integral on x on the right with a function of x only. We can solve these integrals. If we know how to solve them, we solve them. And then we find some relations between y and x's, and then we isolate for y. We find this will allow us to integrate and solve for y. After doing that, you will find the solution, which is y of x. Okay? All right. Now, we will do examples to see what this is like. This is the proper way to do it. The fast way to do it, again, you tell your pure mathematician friends to look the other way. I will also look partially the other way while I do it. So I have that this would be, I can move the different, I can multiply by the x. Oh my god, this is so horrible. I can multiply by the x both sides, and I get my dy equals mx dx. Oh geez. And then I say, yeah, I integrate that, right? And then I get the same thing. Well, careful, right? I mean, it feels that we're doing something wrong with the first one, because first of all, we're multiplying by a differential. What is that? This thing does not, it's not a fraction. The derivative is not a fraction. Doesn't work like that. You cannot really multiply by a differential, strictly speaking. Now, anyway, also it feels that we're integrating with respect to y on the left and with respect to x on the left, so we're not doing the same thing. No, we are doing the same thing. We're integrating with respect to x on both sides. This is more like a recipe to do it fast, right? We know that the real math is done on that side. But you see, we arrive to the same step, just in one step. We arrive to the final expression by moving the differential there. Again, you have to kick out the pure mathematician from the room. In fact, they will kick you out if they see you doing that. So anyway, you know what I mean, right? Hopefully. So this is the way to solve separable equations. So it's the problem is gonna be reduced to integration, and we're gonna see some examples. All right. So we're gonna solve this simple one. We have y dot equals y times x. So this is an ODE, independent variable x, dependent variable y. So what we want is y of x. All right. And the general solution means that we want all the infinite possible solutions we will have. All right, it is a separable equation. We can write all the y's on the left. Remember, this thing is the same as dy dx, right? Anyway, so we put all the y's on the left, and then we have an x on the right. Now, again, fast way and slow way. So if we integrate with respect to x on both sides, this thing is gonna give me a log of y, and this thing is gonna give me an x squared divided by 2 plus a constant. Was that too fast? Where did the log come from? Okay, let's see it with more steps, all right? Just for the first time. But every time, I want you to learn that every time we have to integrate that, we're gonna have a log in there. Let's see it in detail. So we have here so how did we get there? From this equation that we have here, we had dy dx is equal to yx. Right. Then we do what we know we have to do, and then we get dy divided by y, all the y's on the left, x dx, all the y's on the right. We integrate. This is the fast way, of course. You know how to do it properly, right? To do it properly, what you do is integrate with respect to x on both sides. All right, and then you get the same thing. And the integral of 1 over y is the log of y. And then the integral of x dx is x squared divided by 2. Now, of course, it's an indefinite integral, so there's a constant that is missing. We call that constant d here. And just to call it something, it's a real constant. Now, interesting enough, this constant that we have here, right? I put it out of the integral over x, but of course there's a constant integral over y. What I do is I combine the two constants into a single constant d. You can write, I don't know, f here plus g here, and then you call d f plus g. It's an arbitrary constant, right? So we can put all the constants on the right. That's how I got that out of the integration. This integral gives me the log. This integral gives me x squared divided by 2 plus d. All right, nice. So, what do I do now? Now, if you remember properly, this only gives you the absolute value of y. So in fact, this is the log of absolute value of y, okay? Let's just keep that in mind for now. So if I take exponentials, oh, by the way, note, my log is the log, is the natural log. This is also grown-up notation. If I write log, I mean is the natural logarithm If I want to say base 10, I would write log 10. I will never write log 10 in this course because we're going to work with, they're related by a constant. So I'm not going to write explicitly ln. I'm going to write log for my natural log. If I want to write a basis different from e, this is the inverse. Log is the inverse function. So log if I write log of e, that is 1. Okay? All right, I take exponentials to undo the log. So if I take here, I take the exponential of log modulus y. It's equal to x exponential of x squared divided by 2 plus d, or e times d. All right? Okay, so the exponential undoes the log, and I get modulus y. It's equal to e d exponential of x squared divided by 2. Now, this is a constant. The exponential of a constant is actually a positive constant, but this is an absolute value, so actually y is equal to plus minus e to the d e to the x squared divided by 2. Okay, nice. So I call this plus minus ed a constant c that can be any number, and the solution is that y is equal to some constant exponential of x squared divided by 2. And that is the solution. That is y of x. Quick recap. We started with this equation. We put all the y's on the left, all the x's on the right. We integrate both sides. The integral of that basically is the logarithm. The integral of the right is s squared divided by 2 plus d. I take exponentials to undo the log. That gives me a to the x squared divided by 2 e to the d. That gives me that the absolute value of y is e to the d exponential of x squared divided by 2. But now, of course, the y, this is always, the exponential of any real number is always positive, okay? But then this is the absolute value, so it could be positive and negative. So what I do is call this, all the possible values, positive or negative. So ed, I call it a new constant, c, that is any real number, and that's the solution to the problem. All right, so you know how to solve that equation now. Let's do another example. Right, so we have the general solution now. We're asking for the general solution to this equation here. Now, again, this is a first order ODE, and it looks separable to me. I can put all the x's here and all the t's on the other side. So let's write it explicitly in terms of the derivative for now, right? The independent variable is t, the dependent variable is x in this case, so the solution would be x as a function of t. All right, I have that on the left, that's equal to 1 plus x squared e to the t. Definitely, I can put all the x's on the left, all the t's on the right. So I get this thing, dx, I'm doing the fast way, 1 plus x squared equals e t dt. There's an e. All right. Now, we integrate both sides. If we integrate both sides, we get dx 1 plus x squared equals integral of et dt. So do you remember what this integral was? This integral is one of those that you need to know what it is. I'll give you some time to think about it. It's the arctangent. Remember that? This is arctangent of x. So on the left I get the arctangent of x. And on the right, well, this is an exponential. It's one of the most difficult integrals ever. The integral of the exponential is the exponential itself. So this is et plus a constant. Let me call it c. All right. So now what we do is separate x. How do we undo the arctangent? Well, taking the tangent, of course. The arctangent is the inverse function of the tangent. So the next step, we take tangent on both sides. On the left we get x. On the right we get tangent of et plus c. And that is the general solution that we're after. That's x of t. All right? Well, let's do another. All right, so we have the general solution of y prime equals c y squared x. This also feels very separable. We can put all the y's on the left, so again, let me just write it like for clarity, dy dx equals 6y squared x. Dependent variable is y, independent variable is x, the solution would be y of x. Alright, so we put all the y's on the left, all the x's on the right. So if we do that, we get dy divided by y squared, okay? And then I put the 6 on the other side just because I want to, 6x dx. Alright, we integrate both sides with respect to x, you know what I mean, right? We integrate both sides, and we get dy y squared, alright, equals integral 6x dx. Well, that's very easy. On the left hand side, the integral is minus 1 over y, and on the right hand side is 3x squared plus a constant. All that is left to do is find y as a function of x. So we just invert the equation, and we get that y it's equal to y of x is 1 over, what do I have here? Yeah, so 1 over, with the minus on the other side, so maybe I can write minus 1 over 3x plus c. All right, and we're done. This is the solution to this equation. Easy, right? Okay, let's do another. All right, so the general solution to this one. This is another separable equation. All right, so let's see it. We have to put all the y's on the left, all the x's on the right, same as before. And what we get is 2y minus 4 dy is equal to 3x squared plus 4x minus 4 dx. That's pretty simple. We integrate both sides. So if we integrate both sides, what we get is y squared minus 4y equals x cubed plus 2x squared minus 4x plus a constant. Right, we need to solve for y though. So how do we solve for y? Well, that's easy. It's the quadratic equation, right? To get a function of x, we need to use the quadratic formula. So remember, the quadratic formula tells me that y is equal to minus b plus minus square root of b squared minus 4ac divided by 2a, right? Well, those are the terms of the quadratic equation. So if we substitute in this case, we know that b is 4, a is 1, and small c is all this thing with a negative sign. Anyway, so if we write it, we get that y of x, the solution, it's equal to 4 plus minus square root of 16 plus 4 times x cubed. I write a plus that cancels the minus that goes by putting this on the left hand side, plus 2x squared minus 4x, plus c or minus c, it doesn't matter, it's a constant. So in this case, it doesn't matter what sign you put in. I could have called it, I can change the sign of the constant, no problem, because it's an indeterminate constant, okay? If when we see initial value problems where we actually assign a number to that, somehow we compute particular solutions and we find a number for a value for that constant, in those cases, that c will have a value. But right now doesn't have a value, it's in real numbers, so could be positive, negative. If I put minus c, it's also all the real numbers, huh? So it's the same. Anyway, I'll take minus c, not to make too much of a mess for you that you're right the first time exposed to this, so hopefully that helps. Divided by 2, so we can simplify it because 4 divided by 2 is 2, so this is 2 plus, so let's just write y of x equals, because that's going to be the solution. 4 divided by 2 is 2 plus minus 2 inside the square root enters like a square, so 16 divided by 4 is 4, so 4 square root of 4, then plus 4 divided by, so in the square root that enters like the square, so 4 divided by 4 is 1, this is plus x cubed plus 2x squared minus 4x minus c. There you go. This is the general solution. We made it. There's another one. All right, let's do another example for now. So we do this one now. So, another separable one. We can put all the y's on one side and all the x on the other. You can tell this y goes here and all that is left is x's. All right, so let's do it. So we have here dy divided by y cubed equals x divided by square root of 1 plus x squared. All right. Cool. So we need to integrate this. So the left hand side is really easy to integrate. So if we integrate this, sorry, I forgot the dx. All right. So if we integrate this, maybe I'll write it here. I'm not too confused too much. You're not used to that notation yet. You will become though used to this notation. All right, people. So let's integrate both sides. The left hand side is very easy. The left hand side gives me minus 1 divided by 2y squared. The right hand side is also very easy because actually this is a square root, right? This is the derivative of the square root. If you remember, the derivative of the square root goes exactly like that. Or in other words, this thing is the derivative of the inside. If you don't remember how to integrate, please review it because it is important, okay? And I mean, it's basic stuff. This integral, if you do it, is going to be the square root of 1 plus x squared. All right, this is an example of an integral where you have the integral of, you have a derivative of some function of, let's say, derivative of g of x, g prime of x dx. If you have that, then you know that this thing is equal to f, or plus a constant of course, to f of g of x plus a constant. And you can tell that x root of 1 plus x squared is precisely the derivative of this guy here. So this is one of those cases. So go back to your integration, and if you don't remember, please make sure that you remember. Okay? Anyway, you can quickly check that that's the case, right? Take a derivative here. If you take a derivative of that, derivative of the root is 1 over 2, the root of the argument, but then outside the derivative, multiply the derivative is 2x, that cancels the 2, and that gives you exactly this. 2x is 1x is remaining. Hopefully you see it. If not, if you're having trouble with all this, review your integration, because all the problems that you can face here are problems related to integration. And if after reviewing your integration you still have problems, come talk to me, please. Okay? Well, come talk to me, come to the live sessions that we have. All right? Okay, so hopefully this is clear enough. It's just integration. I would not be too worried about not being able to integrate. Keep in mind that all the assignments that you will have, including the final assessments, are at home. You can do your integrals by hand and show me your integrals, but you can also check them online, because Wolfram Alpha does all these integrals for you. So don't use Wolfram Alpha just to solve them, okay? Solve them yourself and use Wolfram Alpha to check. So it's not gonna be a problem. The integration is not gonna fail you, all right? Okay, so hopefully that puts your mind at ease. All right. All right, so now we invert this relationship, which is easy. So what we get is that y squared is equal to minus 1 divided by 2 root of 1 plus x squared plus c, right? Now, a little note here. 2 times c is also a constant, so I can reabsorb the 2 in the integration constant, and I can say this is just twice root of 1 plus x squared plus c, since c is an indeterminate constant. If you want, I call this constant c prime, or maybe d here, and I define a new constant c that is 2d. Typically we won't be doing that. It's c, and I reabsorb the 2 in the constant. All right, we still need to take a square root, and then what we get is that y is the square root of minus 1 divided by 2 root of 1 plus x squared plus c. Keep in mind that this solution will not be existing everywhere. Whenever this is a negative, that goes for the other one. When you have square roots, whenever this value of the square root is negative, then this doesn't have a real solution. But of course, that depends on the constant c. So depending on the value of the constant c, you will get that the range of validity of this function will be different. But this is the formal solution and this is the general solution. This could be positive or negative. If this c is negative and larger in absolute value than this for all those x's, this is going to be well defined. All right, cool. Keep in mind as well that that could be a negative branch of the square root as well. If you were a negative branch, you get also values for c that it works when this c is positive and larger than this. But then again, what you have to concern yourself about is this formal solution at this level because we're finding only the general solution. All right, let's do one last more. This one, find the general solution of y dot equals exponential of minus y times 2x minus 4. All right, so this is a separable equation again. The y is on one side, the x is on the other side. So we get e to the y again. If this helps you, of course, you can always write this as dy dx. It allows you to see that the dy stays here, dx goes there, without mathematician looking at us. And then what we get is that e to the y dy, it's equal to 2x minus 4 dx. All right. Now we integrate both sides. That's an easy task, okay? So the exponential gets the same, the exponential. And here we get that this is x squared. Okay, we integrate, right? And this is x squared minus 4x plus a constant. Now we need to solve for y, and that gives me that y is equal to the natural logarithm of x squared minus 4x plus c. And that's the general solution. All right, wonderful. This is the last example we're gonna see, but let me introduce the notion of initial value problem. All right, so let's modify the problem a little bit, like that. So now it's very similar. We say solve the initial value problem, and we have the same differential equation, but instead of wanting the infinitely many solutions for all the values of the constant that are available, we want a particular solution, the one that satisfies that y of 5 is equal to 0. So this would be y of x, but we actually want to find the solution in particular, y of 5 is equal to 0. What does that mean? It's determining the value of the constant to get the particular solution that satisfies this initial value problem. All right, so now the final solution of this is not the general solution, it's the particular solution. Let's impose it. Y of 5 equals 0. That means that y is 0, y is 0 when x is 5. Let's impose it at this step because it's easier than imposing it here. So at this step we impose that y is 0, e to the 0 is imposing y equals 0, x equals 5. On here we get here e to the 0 equals to 25 minus 20 plus c. Nice. So this is a 1. This is 5. So nice. This is a minus 4 on the other side. So we get c equals minus 4. And there you go. That determines the solution. So the solution we have, substituting the general solution, the solution of the IVP is that y of x is equal to the log of x squared minus 4x minus 4. And this is the solution to the IVP. As you can tell, solving IVPs for first order equations is pretty easy because it means substitute the values of y and x that you're given as your IVP, find the value for the constant. All right, this was your first, separable equations are somewhat boring in the sense that it's just integrating, which is boring. We're gonna see other ones, right, where things are gonna get more spicy. But this was your proper first lecture on actually solving differential equations. I hope it was understandable enough, but if not, that's why the in-person sessions are for. So please do come and do ask, and I'm here for you. All right, so that's the end for this video. Thank you.